For centuries we have relied on classical computers to power our world. These machines, while powerful, are limited by the laws of classical physics. Today we stand on the brink of a new era, an era where the strange and counterintuitive laws of quantum mechanics are harnessed to create a new breed of computers: quantum computers. These machines have the potential to revolutionize fields such as medicine, materials science, and artificial intelligence. Unlike their classical counterparts, quantum computers take advantage of the unique properties of quantum mechanics, promising exponential leaps in processing power. The journey into the world of quantum computing begins with understanding the fundamental principles that govern the quantum realm. These principles often defy our everyday intuition, as they describe a world where particles can exist in multiple states at once, and where distant particles are mysteriously linked. Yet these seemingly bizarre quantum phenomena hold the key to unlocking unprecedented computational power. In the quantum realm, the familiar rules of classical physics no longer apply. Here, particles like electrons and photons exhibit both wave-like and particle-like behavior, a concept known as wave-particle duality. Imagine a tiny marble rolling down a slope. That's a classical particle. Now picture a wave rippling across a pond. That's a classical wave. In the quantum world, particles behave as if they are both, a marble and a ripple, simultaneously. Another crucial concept in quantum mechanics is superposition. Imagine spinning a coin and not letting it fall. It's both heads and tails at the same time until it settles. Similarly, a quantum particle can exist in multiple states simultaneously. This ability to be in multiple states at once forms the bedrock of quantum computing. Entanglement, another cornerstone of quantum mechanics, links the fates of two or more particles. Imagine two coins flipping and landing the same way every time, even if they are miles apart. This is entanglement, a bizarre connection where the state of one particle instantly influences the state of another, regardless of the distance between them. This seemingly spooky action at a distance, as Einstein called it, is a key resource in quantum computing. At the heart of a quantum computer lies the qubit, the quantum equivalent of a classical bit. A classical bit can be either a 0 or a 1, like a light switch that's either on or off. A qubit, however, can be 0, 1, or a combination of both simultaneously due to the magic of superposition. Think of a qubit like a dimmer switch that can not only be on or off but also anywhere in between. This ability to exist in multiple states simultaneously allows a single qubit to store and process vastly more information than a classical bit. The real power of qubits emerges when we link them together. Two entangled qubits don't just store two bits of information, they store information in a combined system. This exponential increase in computational power with each additional qubit is what makes quantum computers so extraordinary. Imagine searching a maze. A classical computer tries each path one by one until it finds the exit. A quantum computer, using superposition, explores all paths simultaneously. It's like having a team of explorers, each taking a different path, all at the same time. This ability to explore multiple possibilities simultaneously is what gives quantum computers their incredible speed advantage for certain problems. Instead of working through possibilities one by one, they can analyze all potential solutions at once, making them exponentially faster for specific tasks. This power of superposition allows quantum computers to tackle problems that would take classical computers billions of years to solve. Imagine trying to find the proverbial needle in a haystack the size of the Earth. A classical computer would be searching for millennia, while a quantum computer could pinpoint the needle in a fraction of the time. Section 5. Entanglement. A spooky connection at a distance. Entanglement, often dubbed spooky action at a distance, is another key to the power of quantum computers. When qubits become entangled, their fates are intertwined. Measuring the state of one instantly reveals the state of the other, no matter how far apart they are. Imagine two entangled coins. Flip one, and it lands on heads. Instantly, you know the other coin has landed on tails, even if it's on the other side of the world. This seemingly impossible connection is what makes entanglement so powerful and so baffling. In a quantum computer, entanglement allows qubits to work together in unison, like a choreographed dance. This harmonious collaboration amplifies their computational power, allowing them to tackle complex problems that would be impossible for classical computers to solve. Section 6, Quantum versus Classical, a tale of two computers. Comparing a quantum computer to a classical computer is like comparing a supersonic jet to a bicycle. Both are modes of transportation, but their capabilities are vastly different. Classical computers excel at everyday tasks, from browsing the internet to running spreadsheets. They process information sequentially, like following a recipe step by step. Quantum computers, on the other hand, are like high-performance race cars, designed for specific, complex tasks. They are not meant to replace classical computers but to complement them, tackling problems that are impossible for even the most powerful classical computers to solve in a reasonable time frame. While classical computers struggle with problems that involve vast numbers of variables, such as simulating complex molecules or breaking encryption codes, these are the very problems where quantum computers shine. They offer a fundamentally new way of processing information, opening doors to solving some of humanity's most daunting challenges. Section 7. Applications of quantum computing, a world of possibilities. The potential applications of quantum computing are vast and span numerous fields. In medicine, quantum computers could revolutionize drug discovery by simulating the behavior of molecules with unprecedented accuracy, leading to the development of new drugs and therapies. In materials science, quantum computers could help design new materials with tailored properties, such as superconductors that operate at room temperature, revolutionizing electronics and energy transmission. In finance, quantum computers could be used to develop more sophisticated risk management models and optimize investment strategies. Section 8. Challenges and the road ahead for quantum computers. Despite their immense potential, quantum computers are still in their early stages of development. Building and maintaining these machines is a formidable challenge. Qubits are extremely fragile and susceptible to environmental noise, making it difficult to maintain their delicate quantum states. One of the main challenges lies in scaling up the number of qubits while maintaining their stability and coherence. Imagine trying to build a house of cards in a hurricane. That's the level of precision and control required to build a large-scale, fault-tolerant quantum computer. Another challenge lies in developing quantum algorithms, the software that runs on these machines. Designing algorithms that can effectively harness the power of superposition and entanglement is a complex task that requires a new way of thinking about computation. Section 9. Conclusion. A quantum leap into the future. Quantum computing is not merely an incremental step in computational power, it represents a paradigm shift in how we process and understand information. While significant challenges remain in building practical, large-scale quantum computers, the progress made in recent years has been remarkable. As we venture further into the quantum realm, we can expect to see transformative applications emerge, revolutionizing fields such as medicine, materials science, and artificial intelligence. The future of computing is quantum, and it holds the potential to reshape our world in profound ways.